In this video, we'll really begin our study of calculus. Now, as I said on the introductory video, this does take a little bit of time to develop the ideas and the concepts. We are going to start with section 1.4, but in this section, we start to introduce some ideas and concepts, and we start to hint at the answer. But again, this is not something we're going to fully answer until we get into chapter 2. So, let's take our time with this, and as you go through this section, to realize that we're going to talk a lot about slope, we're going to talk about some tangent lines, this idea of velocity, a few other applications that we'll try and work in as well. But again, this is mostly just a little bit of exploration, and then our next section, 1.5, when we start talking about limits, that's where the first bit of the real work starts off. So again, we're starting in 1.4, but just before I jump in, what's at the beginning of chapter 1? Well, a little bit more review. Chapter 1, they do 1.1, the author does start off talking about functions in general. He goes into a little more detail than I did in the review video. He also establishes that it's not just equations and graphs, there are also charts and just looking at functions as sets of XY pairs. So that might be a good section to read through just as a few reminders. 1.2, he gets more specific with functions. 1.1, he also talks about some of the properties of symmetry, of increasing, decreasing. 1.2, more functions, more of the specifics of functions. What does it mean to be an algebraic function, a trig function, a root function? So there's a few other terms there. Again, doesn't hurt to look through. The straight line stuff, the y equals mx plus b, the reminders of slope. We are going to talk a lot about straight lines, so that might not be a bad thing to look over. And then 1.3, he starts addressing more of the graphing, how we could make new functions from old ones by combining them, adding them, multiplying, composing, that the graphs, that this might be a shift up. If we have plain old y equals x squared as a parabola, then x squared plus 2 shifts up 2 units. X minus 1, the quantity squared, shifts right 1 unit. A negative in front of the x squared reflects across the x-axis. So again, lots of pre-calculus, lots of things to mention, but it's all just review. We'll see little bits of that. It doesn't hurt for you to read through. As I said in the introductory video as well, it's good to start reading the book. This author does a nice job, so it really doesn't hurt to at least flip through those sections, start to get used to him a little bit before we get too deep into the class. But now, having said all that, now we can really start section 1.4, the tangent and velocity problem. So the first thing we have to discuss is this concept of a tangent line. The idea of a tangent line comes from the idea of circles. So here's my very rough, poor circle. But when I look at a circle, the idea of a tangent line to a point is to just take some point, so I'll pick this point right over here, and to draw the line that just nicks that point and doesn't really hit the rest of the circle. So I could draw lots of lines through this point. There's tons of them. But the line that just nicks the circle, that just skims its edge, would roughly be this line. So that would be the tangent line to the circle at this exact point. But if I did it maybe over here, this would roughly be the line. Oops, sorry, that skipped a little. There we go. That would be its tangent line. Over here, and that would be its tangent line. So I could draw that tangent line pretty much anywhere over in this. I can draw it anywhere on this circle. Pick any point and I can draw that line. And again, we will talk about slope. That has a positive slope, that has a positive slope, that has a negative slope. That line is more positive sloped than this one is. Again, those are other reminders that come up, but just first things first, what is a tangent line? But now, one of the big things we are going to discuss is not just a random tangent line, but a tangent line to a curve. Not to a circle, but to a generic curve. So you'll notice if you're following along in the book has similar pictures and discussion, And as I said in the intro video, I try not to do problems that are exactly the same so that the book offers you extra examples to think about, to work through if you need them, little extra preparation and study before you jump into the homework or to help with the homework. But for this part, we really kind of have to be on the same page to get these first ideas established. So there's my circle, draw my tangent lines anywhere I want. But now, if I just draw a random curve, so let's do, there we go. There is some function f of x, which at this point is not too important. But just realizing, as I said in the introduction video, we're mostly going to be focusing on functions in this class. So just to start off with a function. But now, this idea that I was talking about up here, when I draw a line, we can't draw the whole line because the line continues forever in both directions. So we always just draw this little line segment and that we understand the idea that this continues. But in a circle, if you draw this tangent line forever, it never ever hits the circle again. But when we get to something like this, we have to realize that we might hit the graph somewhere else when we focus on a tangent line. So if I focus on the tangent line to this function f of x right here at this point that I just highlighted, I'm still trying the essence of what I was doing here. I'm still trying to get that line that not just goes through this point, but that just skims the outside of the curve as it hits this point. So for this one, it would roughly be about here. That's actually a pretty good line. Really just hitting that point on the curve, but not hitting anywhere else. But now to realize, if I extend that segment, well, up here it's not going to hit the graph at all, but if I extend it, I'm going to hit the graph down here. So that's just a possibility we have to realize that could come up when we're looking at just any old regular curve, but the idea, again, not just a random line through this point, the idea of just nicking that line. So maybe if I pick a different point over here, that line would almost be, or probably would be horizontal. If I pick this point over here, then I would have this positive, I'm a little off there, that's a little better. This positively sloped line right about here. So once again, just like we saw in the circle, I could kind of pick any point I want, and I could find, and I can draw and see the tangent line. So, now let's already move right into an exercise. And like I said at the beginning of this video, this first is just a lot of motivation. We're kind of jumping into a problem without too much guidance. So just pick up on the little ideas. See the little ideas of slope. That's what we're going to be talking about a lot throughout this. And then we'll start to get into the little bit of the applications to go with it. And then we're going to realize that we need more information, more tools. And that's what will lead us into section 1.5. And then after we discuss that idea, which is formally called a limit, then after we get all of those facts, then we can come back and answer all these little questions that we're starting here. So, continuing, I start off with an example. Let's look at a nice simple function that most of us are pretty familiar with, y equals x squared. And I want to look and concentrate on finding the slope of the tangent line to this curve at the point 1, 1. So just first thing, the y equal x squared. Again, quick graph. You'll notice as we go along, we do have to deal with graphs a decent amount through here. But as I said in the introductory video, we don't need graph paper. We just need to make a little scale that we could follow. And as long as we try and be consistent with it, that'll be fine. So I'm just going to draw a very rough, messy parabola. And that there is the point we're focusing on. Oops, right there. There is the point we're focusing on, 1, 1. So I want to find the slope of the tangent line. So I've got my rough picture, and roughly that would be the line. So just thinking about slopes of lines, like I was saying up here, just the fact that it's got this upright trajectory to it, I know the slope is positive, but that's basically it. If I did draw this on a piece of graph paper, had a better scale, I could do a better job approximating exactly how positive this is. Is the slope positive 1, up 1, over 1? Is it positive 2, positive 10? Well, again, the graph might help us with that. But what we're going to immediately move in is to realize that this is a little bit troublesome. Because at this exact moment right now, again, without having a better scale, I can't really do a good job of finding that slope. So I'm going to divert away from this for a moment. Instead of focusing so much more on the slope of this tangent line, let's have another quick diversion. Let's come back up to the top and let's talk about the idea of a secant line. Now, I know some people are already looking at the words tangent and secant. Those are trig functions. There are connections to these geometric ideas to those particular trig functions, but don't get into that right here. That doesn't help in any way. Just to realize they are trig functions, there is a connection, but right now we're looking at the geometry, the geometrical perspectives we're getting. So a tangent line to a curve, whether it's a circle or a curve, is just this idea, pick one point, the line that just nicks that. But a secant line always takes 2 points, and it's the line drawn through 2 points, whether those 2 points are on a circle or a curve. So if I picked these 2 points, that would be the line between the two. If I pick these 2 points, that would be the line between the two. And I could do the same thing down here. This point and this point, I would have a long line like this. This point and this point, I'd have a line. Again, it's not about how long the line is, but just how far the points are to make sure that we're connecting and getting that correct shape. So, why am I bringing up the idea of a secant line here? The reason is when I come down here, I don't have enough information. Because when we talk about slope, here's our first good reminder. The formula for slope that a lot of people remember. This is, for some people, especially physics, they're very familiar with the idea of delta y over delta x. The delta in math and science always stands for change in. But if you're not so familiar with this, no big deal. You're probably more familiar seeing it in this form. And the whole basic behind this, to find the change in y over the change in x, the concept of the rise over the run. All these little old ideas about straight lines and slope, but that idea always relied on having 2 points. By having the xy pairs for 2 points, we could plug them in to then find the slope. And that takes me back to here. My problem with this tangent line is I only have 1 point. How do I get a second point to figure out the slope? And this is where the trouble comes in. I'm going to start off in almost a terrible way. I'm going to change color on my pen here just so we could see this a little bit better. I'm going to go to a second point here. Another point on this curve. This is 1, 1, and this would be the point 2, 4. And if I draw the line, the secant line, between those 2 points, not in a very good way, but that line slightly mirrors this tangent line. So if I could find the slope here, so I'm always going to use 1, 1, but now as I start moving into secant lines, I need a second, so I'm going to use 2, 4. So I'm not going to get the slope of the tangent line, but the slope of the secant line, well, I'll do y minus y, 4 minus 1, over x minus x, 2 minus 1, and I'll get 3 over 1, which is 3. So we found the slope of this first red line is 3. But, as plenty of you are probably already saying, so what? How does that help? This red line is clearly not the same as this black line, so why is this slope really going to help me with this slope? So let me even make that note. So this is the tangent line, and the slope of the tangent line. That's really what we're looking for here. Okay, well, here's the thing, everybody. I can do better. Instead of going so far away, instead of going out to the next x coordinate, which is 2, what if I go a little bit closer? What if I pick my next x coordinate is here? So here at about 1.5. And now I'd have my second point here. So when I do this again, now let's look at our second point, and we're still going to use 1, 1, but now my second point, I'm going to use 1.5, and when I plug that into the equation, I'll get 2.25 for the y. Oops. So now, when I do this one, now I'll still do the same slope formula, but now I'll get 2.25 minus 1, this y minus this y, all over this x minus this x, 1.5 minus 1. I know we're getting some ugly decimals, but again, calculator's fine if you prefer, just to get this. So I get 1.25 divided by 0.5, and that gives me a slope of 2.5. And if we really look at it, I can't draw too much in here. My picture's going to get messy. But again, if you're following along in your book, this first example, the book is doing almost the exact same thing and just has a little more space to just slide their pictures in. But if we looked at this second secant line, it is a much better, closer approximate to this tangent line. So this slope is a better, this slope is a better representation for the slope of the tangent line than this first one was. And guess what? If I want to do better, I just get closer. So I went from my second x value is 2 to my second x value is 1.5. We'll do this 2 more times. We'll next do 1.1, which has a y of 1.21. And then we'll finish with 1.01, which has a y of 1.0201. So I'm still doing the same thing, everybody. Slope of the secant, but now this y and this y. So I'm just already going to start doing the arithmetic. 1.21 minus 1, all over 1.1 minus 1. And we get a slope of 2.1. And the last time when I set up this last one, this y minus this y, I get 0.0201 divided by this x minus this x, which is 0.01, and I get a final slope of 2.01. And every time I got closer, this second point, this was my secant line, much closer to the tangent. But then x is 1.1. This is my second point. That secant line is almost right on top of this tangent line. And this last one, I can't even fit that in with my pen. This is just too fat of a point to actually make that second mark, so that this secant line is essentially the same thing as this tangent line. So what is the point of all this? You could keep going. The book then starts doing it on the other side. Well, what if I pick this point that's far away, but then pick this point that's closer, and then this point that's closer? And what they end up with is that the slope, when I pick x's closer to the original from this slide, well, this is my final slope. I started at 3, then 2.5, then 2.1, then 2.01. If you do it the other way, you get slopes of 1, then 1.5, then 1.9, then 1.99. We're honing in towards a value of 2. And that's what the slope of this tangent line actually is. Now, we're not going to be able to prove that for a little bit, but that's what the tangent line really is. And this is that first big concept. What we are doing here, this idea of getting closer and closer to a point without actually getting there, right? I can't pick my second x value as 1, then I've had the exact same point back. But by letting x be 1.1 and then 1.01, I'm letting my second x value approach the value of the first x value. And this is the big picture concept of a limit. But not just the limit itself, this is already starting to address what the limit actually does for us. And that with a limit, we can go from finding a slope of a secant line to the slope of the tangent line. So there's a lot there. There's a lot to be said just from that first page. And like I said, it's very easy to just, okay, we're talking about slope and not fully understand why yet. And that's perfectly fine. This is still just an introduction. But now let's already start to get some of the purpose. Why do we care about the slope of a tangent line? Why we set up a whole section designed to point us in the direction of how we would do that, unless we had some real purpose, some reason that we care. So what is the reason that we care? And here it is, everybody. We're going to start looking at the velocity problem. But before I even do that, I'm just going to draw a random graph. And don't even care what the units are. I'm only in technically the first quadrant. You'll see a lot of real applications. You know, you can't have negative x as negative y. Sometimes they make sense. Other times they do not. But what I want to now do is think about the units that go with something like this. So maybe we're measuring the amount of air in an oxygen tank, like if we're scuba divers or if we work on a submarine or something, and we need to just keep an eye on our air. So our y value represents the total amount of air we have in the sub, and then the x-axis represents, maybe this is the time we are submerged. So with that in mind, it kind of makes sense this would go down. The longer we're underwater, the more air we're using. And maybe there's a point, how many people are on the crew, maybe we let some more people on, something like that, so we went down faster. Maybe this is a point where people were sleeping, so we weren't breathing as much, whatever the reason. But overall, how much air we have over how much time has passed. So if I look at the slope of a tangent line and think about the units, wherever that tangent line is, that slope is again going to have units from y divided by the units from x. So if we think about the example we were just talking about with how much air, however we measure our air, maybe we have like cubic meters of oxygen, and how are we measuring our time? Maybe this is measured in days or hours. And if we put that together, we get a rate of time. And that rate would represent the rate at which we are using or gaining or losing whatever this quantity is with respect to this quantity. So again, in my air example, cubic meters of air per hour of time. The rate, this would have a negative slope, and that would indicate that we are losing air at that rate. If my graph, I just draw another quick one here, and if this had something more of an upward trend, and in that situation, now I would have a positive slope, and maybe this represents how much money is in the cash register over a shift. If you work maybe at a store or something like that, and hey, we're working, we're selling more stuff, so there's more money coming in the cash register. It doesn't have to be straight up. Maybe I have to pay out a refund or something so that this dips. But same idea. If this represents the money in the cash register and this represents time, then this slope would have units, something like dollars per hour, the rate at which we are gaining money. Now that may not necessarily be profit in that sense. Maybe this just literally is, again, how much money in the cash register. Maybe this is representing our total profit over a period of time. And there are just so many more examples that go with this. So the point of me drawing this out is just to realize that when you start talking about slope of a straight line, which is entirely a geometric concept, but when you start actually putting some application behind it, this slope represents a rate of change. Some of you may have already heard the term the derivative. It's one of the major concepts in calculus, and will have a lot of little ideas that go with it, but one of them will always be the rate of change. the rate you drink water from your water bottle or coffee from your coffee cup, the rate electricity flows into the lights, the rate at which your computer connects to the internet, the rate at which you walk to school, or the rate at which you earn money. All of these things have calculus concepts based coming from that idea that we will call the derivative. Now again, we've got a while to get there, but again, an introductory section starting to show where we are going and giving a little bit of a sneak of how we will get there. So, the last little bit to wrap this up. Just another couple of minutes and we'll wrap up this first lesson. You'll notice this homework is not bad, just a few things trying to reinforce what we were doing, a few problems just focus on getting you back to slope, and then a few word problems. Specifically, we still have to talk about velocity, so just a couple of quick things to finish. So, getting back to this idea of slope. I'm drawing tangent lines in these pictures, but again, I could do the same thing with secant. But here's the big difference, everybody. If you look at the slope of a secant versus the slope of a tangent line, what is the big difference between the two? When you're looking at secant, you'll still get a rate of change. You will still get these types of units, but it will only represent an average rate of change. And that's helpful. There's plenty of sections, if you're in chemistry and you're talking about reaction rates, if you're in biology and you're talking about population growth, average works very well. It really gives us plenty of information to give us the ability to maybe forecast trends, predict how long it'll take to process this chemical, to produce this vaccine, all these different things. Average certainly helps, but there's a lot of times we would prefer the instantaneous rate of change. And that is what we get from the tangent line. Not what happens over a unit of time, but what happens exactly in that moment. Precisely at that moment, what is happening. And now let me introduce the velocity problem. I'm going to do it as speed. We'll come back in a little bit and talk about that velocity is a vector, speed is a scalar. We're not going to do much with vectors and scalars in this class, but just point out there is a little bit of a difference and talk about that. But for this first example, just to understand this as the idea of speed. So speed, as an equation that you probably remember from someplace, is all about distance traveled over time. I mean, some people even distance equals rate times time is one of the main equations that they remember from a science, sometimes it's physics, but other science classes use that as well. Distance equals rate times time, but you could solve for speed in this sense. And think about speed. Think about the units. If you look on your dashboard on your car, you see this mph, which stands for miles per hour. Those are terrible units, everybody. I mean, they're done for our convenience because truth is, just in the United States, we don't do great with science. We really try and find a lot of shortcuts, and that's one of them. It's a quick little mph, miles per hour, but really, formally, miles per is really a math word for divide, hour. That setup of miles per hour comes directly from this equation. How far have you traveled? You don't have to measure it in miles. You could do it in like distance in feet, time in seconds, and then you'd end up with feet per second. You could do things in meters and then minutes and meters per minute. You can keep going, but the idea remains the same regardless. You're looking at a measure of distance over a period of time. So, why am I using this, harping on this? I could do the same thing up here, talking about, distance from home, distance traveled. We started already away from home. We continue to move further away from home. And this tangent line would represent the speed we are moving away from home at that moment. But why do we care so much about the moment? Let's just think about this for a quick moment. If I told you that you traveled 120 miles. I could do a whole little exercise with mileposts that we started on mile marker 106 and we finished on mile marker 226, but I'm just cutting to the chase a little bit more. We traveled 120 miles in 2 hours. Again, I could have done that with time of day. We started at 1:20 and it is now 3:20. But either way, we're getting the basic pieces of information. So if you look at our formula for speed, 120 miles over 2 hours would mean we're traveling at a rate of 60 miles per hour. But let's say you were traveling along on the highway, you're in a 55 mile per hour zone, and you get pulled over by a police officer who tells you you are doing 70 in a 55. You're speeding. Now, if you tell that police officer, but my average speed is only 60 miles per hour, does that really matter? No, and definitely don't do that, by the way. That can very easily be seen as sarcasm and being, a bit of a smart guy. So, don't do that, right? Because realize what you are looking at is your average speed, but what the police officer is looking at is your instantaneous. And even if you're averaging 60 miles an hour, well, in that particular moment, driving 70 in a 55 is, maybe that's not super reckless, but that would be something that is certainly at least a ticketable offense. So it's just a very, very basic, quick example, but just to point out that average, well, hey, again, if you're just taking a long trip and you're thinking, okay, we're traveling an average of 60 miles an hour, we have another 240 miles to go, I should anticipate it should take about 4 more hours. That works. Everything is sound by that math. But then again, maybe you look at that same example and say, well, I was traveling at an average of 60, but now I'm traveling 70. So if I continue at that speed, it'll take me it's not quite 3.5 hours. You could do the arithmetic there. So you could readjust a little bit. And just that first example, that's it. We got through a little bit about slope, some reminders about slope. We saw how some applications, how that can tie in. We already started to establish a little difference between average and instantaneous. And that's everything we're hoping to accomplish in this first section. So again, read over a little bit, start getting into the homework, but don't give yourself a hard time if you're still a little not sure where we're going with this, because we still have a long way to go. And we start that next section with some much more specific information as we start talking about limits.